Okay, let's see. This is working out here. Okay. I don't know. We discovered that the arrangements were these two screens rather than the larger screen, but it works. You can see it. Okay, that's good. So, in our last time, I'm looking at four fundamental features of the world. And this is a set presentation. As I told you, I've done it at Harvard Medical School. I did it at the University of Vienna in Austria and other places to scientists, to audiences that actually were often skeptical. One audience I had was when I was in Harvard. It was about 80 Chinese students, graduate students, and the bulk of them were actually educated in an atheistic context, and so most of them were atheists from all over the provinces. By the end of the evening, especially when we had the Q&A, my friend Li Yi, who had organized this event at the school, discovered that many of them had switched their view as a result of the presentation and the conversation. And they switched their view from atheism to at least a form of deism, if not theism, which was an astonishing, a good night's work, you see, because they'd never heard these arguments before. And I'm looking at what I call four fundamental features of the world. And I'm not looking at Scripture at all. So this is entirely based on science, and it's based upon these features of the world that are incontrovertible. The first of those features, and we looked at this before, I set it up before worldviews and paradigms and implications before I went further from that, the origin of science. And I'd love you to see that. If you missed that session, it's a good background for you to have, because it shows the progenitors of science reveal that it was only created in a context of a theistic milieu. That it had to be that the universe was ordered and rational, and that we could understand this world. And those two basic assumptions, that the world is not basically a chaos, but a cosmos, and that it's understandable, implies an ordering mind, a logos. Secondly, the fact that we can understand it means that we are created in the imago Dei, in the image of that one. My point being that only science never appeared in Greece, China, let alone Asia. The Buddhism and Hinduism were inimical to the scientific endeavor. It was only in that theistic context, and then we looked at the progenitors of science, where they saw that was actually a part of their work as honoring God. And so that was an important principle. But again, I'm only using the science to draw these conclusions, and the idea of sciences that demonstrate that there's actual purpose and that there's the possibility of looking for design. And there are many sciences, cryptography and random number generation and archaeology and insurance claims investigations and others, that you can already know there's a context of design. So you don't want to prematurely eliminate that as a note of explanation. It would be wrong to do so. Instead, science is best defined as go where the evidence leads. And so it's basically a thing of what's called abduction. Go where the evidence leads. And so we've kind of changed the meaning of science. I'm sorry, not late. So we look first of all at the evidence for the universe's beginning after that introductory material I just summarized. And now we're going to be looking at the fine-tuning of the cosmos, and in our time together. And it's exquisitely fine-tuned, and this is becoming a real change in our time, because we'll talk about this in more detail, but the very fact that it is so exquisitely fine-tuned, it's only been grasped in the last few decades how extraordinary that tuning really actually is. Third is going to be biogenesis, the origin of life. And you cannot appeal to any kind of thing like mutations and natural selection, Darwinianism, because you don't even have it alive. It has to be alive for that. So how did you get the first even living cell? How did you get the first protein in the first place, which turns out to be an impossible achievement? And then the fourth feature of the world is information theory. The nature of information is it's really a third ultimate. It is as fundamental as matter and energy. And information transcends the medium itself, because I'll just give you an example of that before we go, and I'll go into more detail later. But for example, if you have a DVD and it has a film on it and another DVD does not, do they weigh different anymore? What is the information? It has nothing to do with matter and energy. It has to do with the organization of that, you see. And so the information is actually a symbolic content that's embedded in it. And so whether it's going to be physical, as if it were as if conveyed by light, or energy rather, or matter, where it's on a piece of paper and you read it, it's the same energy. It's the same information. That's pretty amazing stuff. So having said that, then we went into worldviews and paradigms, and from that I'm going to jump down to where we were before. And but it is significant that the momentum of evidence as time goes by is only toward increasing complexity, elegance, and information, not less. It's getting more of an enigma, not less, as we go by, and that's very important for us to see. So we talked about the evidence for the universe's beginning and went into all these things about that, which was great fun to do. And then I want to now go into the fine-tuning of the cosmos. So again, I'm depending upon your seeing that video if you missed it before. Everyone loves Starry Night. It's just an amazing thing, and there's a whole story behind that painting that's quite remarkable. But the fine-tuning of the cosmos is to be the second feature. And everything has to be just right. And this is a huge topic, and I'm only going to scratch the surface. But everything has to be just right. You have to have the right kind of particles and the nature of those particles. You have to have the right kind of atoms, and you have to have the right kind of molecules. As well, you have to have the right kind of galaxy, the right star masses, the right expansion rate. The expansion rate of the universe is so exquisitely fine-tuned, as we'll see, that it's impossible of achievement. It's just amazing. Moreover, you have to have the right star, and there's no ordinary star will do. It's very, very specified about what kind of a star it would be. Secondly, it has to have the right kind of planet as well. It makes a huge difference. It has to have the right kind of moon as well. And if you add all these things up and really study this, and it's growing as we go by, we discover that it's very much like a clock or a watch that was perfectly organized and finely tuned, and all the parts really work together and fit together in an organized whole. It's not a chaos, but it's a cosmos, and that's really the important thing for us to see. And Carl Sagan, it's interesting, when he wrote about the cosmos, he predicted that we might have billions, remember his billions and billions. We might have millions of habitable planets in our own galaxy. And at that time, there were only a handful of parameters, or about 20 of them, and it was called the Drake equation, and there were 20 parameters. And he wrote a book called Contact. Remember that? And Jodie Foster was in it, and the major theme of that is what a waste. All this stuff if there's only one place where there's life. What if it turned out, though, that the conditions are so elegantly tuned that it required a universe of this size and complexity to create the conditions in which you could have one example of life? And that's really what it's beginning to become, what it's beginning to turn out to be. And so this concept here is, because there are hundreds of now there, at that time, there were, since the 60s when he wrote that, there have been first dozens, then scores, now hundreds of fine-tuning parameters. I'm just going to give you a few exemplars of those parameters. But it's intriguing because, as Fred Hoyle put it, the astronomer, he said, a common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. That's saying an awful lot. And we're not going to go into detail here. Again, it'd be a huge topic. But just to explore just a few of these parameters, how is it possible for there even to be molecules, let alone life? The only way there can be atoms and then molecules is to have the perfect molecular bonding that requires just the right amount of electromagnetic force. If it were slightly larger or slightly less, that force, you wouldn't be able to have atoms at all. And the ratio of the electron mass to the proton mass, that too is exquisitely fine-tuned. Just the slightest bit more in that mass ratio or less, and you could not actually have atoms at all. It's as well, the strong nuclear force has to be extremely precise quotient. And if there were 0.3% stronger or 2% weaker, you wouldn't have life because you wouldn't have molecules. So even all these forces of nature are all exquisitely fine-tuned. With the weak nuclear force, so that was the strong force, but the weak force having to do with the nature of radioactive decay, we're discovering that too has to be finely tuned. Any more or less, you couldn't have stars or galaxies. We've discovered more and more such fine-tuned parameters. So the universe, with its constants, its laws, its initial conditions, requires an exquisite balance to produce the relatively stable environment where life is possible. I'll just illustrate this a bit more with this chart here. So I have that picture here. So it's exquisite. The strong electromagnetic balance, the expansion rate of the universe, the stability of the deuteron, the mass 5 roadblock, this transparency point outward. There's just hundreds of these things now, not just a few. And that's what I'm just trying to stress here. It's exquisite. So I'm going to give you an example of this. Consider the U.S. government debt. Maybe you don't want to consider the U.S. government debt because when you consider it, it's an increasingly depressing topic. And when Bill Ibsen and I created this content, it was a lot smaller than it is now. But at that time, the money to pay for that debt would require, use your mind's eye, 1 square mile of dimes less than 10 feet deep. 1 square mile of dimes less than 10 feet deep. Maybe now it's about 4 square miles of maybe it's now 20 feet or 30 or 40 feet deep, whatever, but it's still, use your mind's eye. So with that idea, I forgot to mention about the neutron. Again, the slightest bit different, and it won't work, yeah. But here's the dimes I was referring to here. But this is nothing in comparison to the numbers that relate to to several fine-tuning parameters. So the maximum, for example, deviation in the mass ratio of electrons to protons, the mass ratio of electrons relative to protons is so finely tuned, it has to be within 1 part in 10 to the 37. Now that's a number with 37 zeros after it, 37 zeros to get your idea, and it's such an incredibly sensitive balance that it's difficult to visualize. So Hugh Ross offered a vivid analogy. So you take these dimes and you imagine that you cover not just the United States but the entire North American continent in dimes, okay? And that not only that, but what you have here is that they go all the way up to the moon, to the height of 239,000 miles of dimes covering the entire. You're getting the idea. And now you pile dimes from here to the moon on a billion other continents, the same as North America. So a billion other continents, the same as North America. Now you're getting close to the point in which you blindfold a friend and ask him to pick out any one of those billion universes, and that'll be a pretty close approximation of 1 part in 10 to the 37. I wouldn't put my money on it. So something has to explain how is it so exquisitely and elegantly fine-tuned. This is only one, as I say, of hundreds of parameters I'm using as an example. It gets even worse because the expansion rate of the universe has to be within 1 part in 10 to the 55. That's 50. That's a zero with one with 55 zeros after it. This is so inconceivable. If the expansion rate was that bit faster or slower, either it would have led to a big crunch immediately, or it would have spun off so fast that you could not have a galactic formation at all. It's that elegant. And we're talking about the probability is so minute that it's practically inconceivable. So imagine a smooth glass surface is the best we can do on this. You have a smooth glass surface, and your job is in a pencil, and your job is to balance that pencil, you see, without any external forces, with this point standing up. Now, multiply that by 1,000,000 pencils. You have to balance 1,000,000 of these pencils. Now you're getting in the ballpark, you see, and it's inconceivable. And there's so many of these factors that go on. Stellar mass is another example. If the ratio of the electromagnetic force to the gravitational force changes by 1 part in 10 to the 40, so again, 40 zeros after that 1 part, then you would either have only small stars or only large stars. You wouldn't be able to have the middle-sized stars required for life. So again, that's yet another factor. We're all in that incredible ballpark there that we're looking at. So when you begin to multiply these together, it becomes extraordinary. We seem to be in a Goldilocks universe. How did it occur this way? You have to have just the right galaxy, too. It has to be a spiral galaxy, not an elliptical galaxy or an irregular galaxy. Only spiral galaxies provide any safe zone for life-sustaining planets, and ours is a barred spiral galaxy. 20% of galaxies are spiral, 60% are elliptical, and 20% are irregular. But again, it has to be and it has to be the right orbit as well. So it's not just that, but it has to be in the right sun. Everything has to be so. So as far as our sun is concerned, it's got to have the right mass, and it needs to be a yellow dwarf. It's not an impressive star, but it's the right one. As compared to Sirius and Betelgeuse and others like that, it's small and not as bright, but it's the right one you need for a lot of reasons. And there are very few like this. And so it has to be a yellow dwarf, and it has to emit the right light, a balance of red and blue, allowing photosynthesis. And the bulk of its radiation is within the visible spectrum, which is a tiny fraction of the electromagnetic spectrum. Furthermore, it has to have the right composition of metallicity for creating terrestrial planets. And in addition to that, it has to have the right orbit. It has to be nearly circular for its temperature stability. And so when we're looking about our orbit around the sun, it has to be that. And so you have all these complex things. So there's a very narrow galactic habitable zone as well, a circumstellar habitable zone. So it has to be, by the way, a single star as well. Most stars are binaries and larger. It has to be a dwarf star. Rather, a bachelor star has to be 1 star. Lots of reasons like that. Because you remember in Star Wars, it reminds me of how we're on a planet and there's 2 suns or 3 suns. Can't happen. And you would not be able, it'd be too unstable. It has to be 1. There's so many details about this that people underestimate it. Furthermore, there's a circumstellar habitable zone, which means the Earth has to be just the right distance from the sun, plus or minus 5% to be exact. Too close, you boil off the Earth's oceans. Too far, water and carbon dioxide freeze, and you have runaway glaciation. Similarly, in addition to that circumstellar habitable zone, there's also a very narrow galactic habitable zone that's been recently understood, and that's intriguing to me as well. So if you look at this galactic habitable zone here, turns out that there's a small, about a 4% range where our solar system has to be in that range. If you get too close to the center, let me go to the next image here, I think. Yeah. If you get too close to the center, you're going to have all kinds of things that are going to be too much intense radiation and other kinds of supernovas and other things of that nature. If you go too far out, you don't have enough metallicity for the kind of star you need to have. So, and other factors that are so there's a habitable zone not only in our solar system but in our galaxy as well. So we keep on discovering these things as we go through. So if you were to just take there are hundreds of these additional fine-tuning parameters, hundreds of them, including the ratio of matter and antimatter. That's another one. Matter and antimatter. The ratio has got to be just perfect. Furthermore, the exact quotient between the expansion energy and gravity. Again, a very delicate balance. The resonance, what's called the resonance energy of carbon, and also the mass density of the universe has got to be very precise, and the cosmological constant, and on and on. So if you keep adding this increasing number of parameters, a very conservative estimate of the probability of having a universe with just a fraction of the right constraints is about 1 part in 10 to the 215. This is an inconceivable number. Anytime you get to 10 to the 50 and above, forget it. It's game over. Even well before that. And so what's intriguing here, but then suppose that there are 10 to the 22 planets. That's a very generous estimate for the number of planets, because there are these exoplanets, as we know. We've discovered thousands of them now in other galaxies and so forth. But if you had 10 to the 22 planets, then we'd subtract the quotient, because the exponential, you'd subtract it, and you'd end up with, okay, now it's 1 chance in 10 to the 193. What happened there? I don't know what happened. My thing did a number on me here. Let me play it again. So my point is, it would be 1 chance in 10 to the 193. It's not looking good. And so at this point, it becomes a desperation here. And guess what the desperate measures are? Because it appears to be a Goldilocks universe, doesn't it? It's called the anthropic principle. The anthropic principle looks like the universe was created for us, that it was created the right conditions just for us. People don't want that to be the case. So they want a way out of it. The desperate measures that people are now taking to avoid the obvious implications is a multiverse. And that is a desperate thing, because you see, they acknowledge that the probability is virtually impossible if there's one universe. So they'll plump for an infinite number of universes and figure, if there's another one, then one of them's going to have a probability, and we just have to win the ones that won the lottery. You get the idea? The problem with that is that, so you have with trillions of universes, the problem is that there's not a bit of evidence, because you have no actual empirical evidence for any such universes. And in fact, you have to deny the most fundamental laws of physics, the first and second laws of thermodynamics, in order to have different laws of physics in these systems. So you're talking about a real stretch, not a bit of empirical evidence for another kind of universe. And at the same time, you have, is that working? Yeah, okay. So there's no evidence for it. It goes against the fundamental laws of physics that we know, the most fundamental being the first and second laws of thermodynamics. And furthermore, even if you could do this, you'd still have to have a universe creator that's fine-tuned, because to crank out any universe would require fine-tuning. So it's right back to the same problem that you had before. It won't work at all. Guess who's living by faith now? You see? Because here the evidence shows clearly that it was a universe that was finely tuned. And the only way they were out of it is this desperate ploy without a shred of empirical warrant or evidence for it. I find that to be a fascinating kind of a thing, that people are willing to do that, because it shows the desperate efforts that people are making to avoid the obvious implications of a designing agency, because they do not want there to be a God, because then they'd lose the illusion of autonomy, and they'd suddenly be accountable, and they don't want God to exist. There's a vested interest, and that's the Romans 1 phenomenon, as you know. So that even though they knew God, they wouldn't honor him as God or give thanks, but they became futile in their speculations, and their foolish heart was darkened. So it was a spiritual issue that led to an intellectual darkness, which then led to a moral decay. So that's intriguing to me. So the way to do this is really using inference to the best explanation. And I love to use Mount Rushmore for this purpose, because it's I've been there. Several years ago, I was asked to speak at the governor's prayer breakfast in South Dakota, and I knew it was in Grand Rapids, so I got to see that. So I accepted it for two reasons. It was only one more state after that I haven't been to out of the 50, and I still haven't been to North Dakota. So if I get a speaking invitation to Fargo or Bismarck, I'm going to go just to round it out. But my real reason for going there is I wanted to see Mount Rushmore, and it was funny to see North by Northwest again, that nonsense and all that, because they have the airport above there and all that nonsense. But it was good fun to be there and to see this. And of course, what you could immediately conclude is that when you look at the Black Hills of South Dakota, we would attribute it to natural causes. But the portion featuring the likenesses of former American presidents George Washington, Thomas Jefferson, Theodore Roosevelt, and Abraham Lincoln clearly implies design. No one's going to attribute the shape of those features to natural causes like sandstorms or erosion. You pretty well know you're dealing with something a little bit more than that. And you wouldn't attribute to a shape to wind and water over great periods of time. We actually recognize the work of an intelligent agent, and that turns out to be Gutzon Borglum, who used a simple multiplication and a plumb line to transfer the measurements on a scale model in the studio to create this thing. It was a really impressive work of engineering that took place from it. It was an enormous endeavor, as you can imagine. It reminds me of so you have some pretty obvious implications there, inference, the best explanation being one of them. And another way I look at this is to use the idea of a turtle on a fence post. There's only three options about this turtle on the fence post. First option, it had to be there. No, I wouldn't say it had to be there. The second option is that a gust of wind or something picked it up and blew it up and made it plop on the top of that fence post. I wouldn't put my money there either. Suddenly, the third option, that somebody took it and put it there, becomes much more reasonable, and that's what we're looking at here when we're considering this kind of a thing. The inference is evident, and so so I find it to be fascinating. So I'll stop there before I go to the next evidence, which is biogenesis. Again, I'm just doing a scratching the surface deal with you, but I hope it's helpful. Does this make sense to you? Yeah, are you sure your numbers are correct?
And those numbers grow.
Actually, as time goes by, it gets more elegant, not less. And the same is going to be true on the microcosm, which we're now about to go into. So when you get into the microcosm, it is even more bizarre, wonderful, and complex. So we're going to be looking at that. But let me see if you have any questions. We have that microphone back there.
Stay totally. To like her dance on.
Ken, do you remember in the old days we all got Time magazine delivered to our houses? Remember God is Dead? 1966, right about the time you talked about how this went crazy, right? The evidence went nuts, right? God has a sense of humor, does he?
Does he not? Yeah. And actually what's happening, and it's a delicious irony, is that he's using science and technology as his vehicle to demonstrate his presence more now than ever before, in spite of the fact that the bulk of the people who are engaged in that are not believers. It's really wonderful to see. So again, though, the issue is go where the evidence leads, and inference to the best explanation is always the way to go. So where does it logically lead? And if it goes to go there. But there's a stubbornness and a rebellion and a pushback. Same here with biogenesis, as we're going to be seeing. Any other questions? So, right? Yes, okay. Grab the mic, yeah.
Here we go. Hey, Dr. Boa. Can you put into layman's terms how the multiverse theory violates the laws of thermodynamics?
Yes. It violates it because you might recall that I did this when we were this a couple weeks ago. The first law of thermodynamics is that the average energy plus mass equivalence density is a constant over time. And so if you look at this, let me just make sure I've got the right thing. Okay, so it's a straight line across. So there's no matter is neither being created nor destroyed. You see, that's the idea. And so for having that idea, you have to have the idea of new creation of matter, new kinds of things coming into being out of nowhere is part of the reason. Another, whereas the second law we commented is intriguing to me because it shows that the average useful energy is diminishing, and it's an exponential decay curve, and it's asymptotically approaching this level here, which is going to lead to what's called the heat death of the universe, you see. And so then what the most interesting is when you put the two together. This is so fascinating to me because remember this, you probably want. This is the most interesting point in the chart. Why is that interesting? Because you can't have more useful energy than there's total energy. In other words, the universe is like you go backwards and it was wound up like a clock. What happened? How did that happen? What was there time before that? Was that point there, T Sabot, was that the creation? But something, you can't go beyond that. Something, because if there was time before that event, something that's universal, that would have access to the entire cosmos, would have to have infused ordered energy into all things that were dying. And so he would have to replace disorder, entropy, with order, and an infusion of ordered energy to sustain life, so there would be no death or diminishment and decline. My own view is such a thing happened, and that the real creation point was here. Now, it's not, I'm exaggerating in the length of time because we don't know how much time it was between the creation and the fall, but there was a period of time between the creation and the fall in which you actually had no second law, in that sense of the diminishment of entropy times zero was actually not growing. So I find that fascinating. So these two things it has ultimately a death. It can't be infinitely old, and it had a beginning, and that to me is a very significant thing. So they're denying, in doing that, they're denying these first principles, because they have to appeal to other kinds of physics, other parameters, other universes, and it denies even what we know. So it's a desperate attempt to deny the two most fundamental laws of physics, to embrace a theory that has no empirical evidence, because you have no, by definition, way of actually seeing evidence for another parallel universe. So it's who's living by faith. Does that help a little bit? Yeah.
Hey, Ken, the just right moon, the just right moon,
yeah,
right? And how it on the wobble of the Earth and the angle of the Earth,
how that whole thing there, because it has to be the moon relative to the Earth is unlike any other of the moons in the solar system. Even though it's not the largest moon relative to its host, to the planet, it's much different. It's much larger, and it has to be that ratio because it creates the right distance as well. And its unique orbit is such that it creates the tidal effects and turns up the materials that actually create the conditions for life, because you need to have the tidal effects in order for the oceans to actually be churned up and so forth. And so it's all part of the whole process, and it has to be, and it's exquisite, as you well know. The rotation of the moon is perfectly synced with its rotation around the Earth, so that you never see the backside. That's why you and I are in that first generation of people who get to see the backside of the moon, the dark side of the moon, which is amazing stuff. But and so forth. And then another wonderful thing about the moon that I love is that while the moon is 400 times smaller than the sun, it's exactly 400 times closer than the sun. Guess what that means? It means that it perfectly occults the sun on a total eclipse, and it's significant that's the probabilities are so diminished, so low. To have a perfect solar eclipse, actually, only when you have a solar eclipse can you actually see the corona of the sun. And we learn more about that through spectrographic analysis than any other way of knowing about the sun. We learned so much about the cosmos and the solar system through the actual total eclipses. So it's like we are in the Goldilocks world in a perfect condition for knowing these things. We also are in the right place in our solar system because we're not around the dusty areas, but we're between the galactic arms in such a way that we can see. It's the privileged planet, as Guillermo Gonzalez calls it, the privileged planet, because it's the perfect place for observing life and observing the outside. If it was anywhere different, we wouldn't be able to see the rest of the cosmos because in any other place, it goes on and on.
Ken, when we hear about the billions and billions of extra galaxies and planets and stuff, the question comes, why did God make all these extra planets and galaxies? And will we ever figure it? Obviously, man will never visit all those places, at least not in the near future. But why did God make all those? Or was it just to boggle our mind?
I think you'll get to ask him that, but
Yeah, I got it. We're not going to figure it out.
Yeah.
I'm still trying to contemplate 215 zeros.
Well, nobody could have imagined it was as big as it is, and the nature of it. And now we see these galactic webs where we have these filaments that are so extraordinarily complex that, in fact, if you were to look at them here, let me see if I can find it for you. Yeah, this is amazing. This study maps the odd structural similarities between the human brain and the universe. It turns out that if you look at the neurons, and then look at the cosmic web here, there's almost the same kind of an image. In other words, the next one here. Go to the next one. Where's the next one? There. You see. So this is the neuronal structure of the brain, and this is basically a map of the cosmology, the spatial distribution of galaxies. Pretty similar stuff. So who could have dreamed or thought that it would be this big and this nuanced and this complex? Remember, we talked about the implications of the WMAP satellite results, rather, microwave. That show that it's exotic, it's expanding. The faster the bigger it's going out there, the bigger it gets, the faster it expands. It's not slowing down. It's mysterious. Nobody understands. So they call it dark energy, and what holds it together, and they call it dark matter. But we don't know what those things are. It's more exotic, more elegant than anyone ever could have dreamed or imagined. So it just gets better. It's just not less. It gets more complex and elegant. So I think that God are going to reveal all that. And it's going to be evident. But it's more amazing and it's terrifying. It's terrifyingly large. Now the estimate is, I've told you this before about the number of galaxies. The estimate used to be about 200 billion galaxies. Now it's closer to 2 trillion galaxies. Each galaxy has about 100 to 300 or 400 billion stars. You do the math, it's far more number of stars in the visible universe than there are grains of sand on all the deserts and beach of the world, and by a factor of at least 10, if not more. So go work that one out. You see. So the idea, the more we're discovering, the greater our vision of God. In other words, science is showing God to be greater and greater and greater. And so you look at that, and it actually becomes more terrifying, more awesome, more incredible than you began to imagine. So I put that together with what I know about special revelation in the Scripture, because the way we learn about His eternal power and divine nature, which is clearly seen, being understood through what's been made. No one could have ever dreamed, though, that it was this elegant, this complex. We know about it now. He's multiplying that and amplifying that, and it's just getting more impressive. Not only in the macrocosm, but we're about to go into in the microcosm. That's my transition to the biogenesis, but I'm out of time. We're running out of time. That's okay. We'll do it, and I'm not in any hurry.
You still got?
I'm going to start the biogenesis. How would that be? Oh, there's a question? Yeah, yes.
This isn't a question, it's just a comment on that last question about why God made the lights. It's in Genesis 1:16, and God made the two great lights, the greater light to rule the day and the lesser light to rule the night, and the stars. And God set them in the expanse of the heavens to give light on the earth, to rule over the day, over the night, and to separate the light from the darkness.
Yes, and then we discover, though, there's a good deal more going on than even that. And so if it's at the very least, it's that. But now we begin to discover, good grief, what's going on? Why so big? And it appears again that to have a cosmos of this nature is necessary to create the conditions where we can have this conversation. There's no other evidence. Yes. Oh, use the microphone. Microphone. We're being good now.
So,
Jess, I've tried to put this in perspective, and just took 14 billion years. It's like 10 to the 15 seconds, and then the universe supposedly has 10 to the 90 atoms. So we're talking numbers that are 10 to 215.
Yeah.
It's
just beyond imagination.
Yeah, it's more than atoms.
Oh, yeah.
In the universe.
Yeah. It just gets more elegant as we go. Well, let me introduce this biogenesis so I feel like I've accomplished something. Yeah. Here we go. So let's go back to him. And this is dragonfly, and with water on its eyes and so forth. Just if you study the dragonfly just by itself, it's beyond imagination when you think, or any butterfly. And the more you look at anything, it's like this. But we consider the exquisite, fine-tuned, complex cell. It's the standard model. So the microcosm, as you know, and I mentioned this before, I should quickly say, it's not an accident that the microscope and the macroscope, which is the telescope, were both invented in the same century, the 17th century, early in the 17th century, right at the time of the so-called Enlightenment, which was really an endarkenment. So at the very point in which people were turning away from a consistent theistic consensus and moving transitionally into a deism and then into a materialism, right at that point, God says, okay, now it's time for me to reveal more stuff. Because as you're turning away, as skepticism increases, I'm going to use science and technology to amplify the evidence. Because God has apportioned the evidence in such a way that there's always enough evidence to satisfy the person who chooses the way of faith, but enough ambiguity to allow the person who rejects it to have rationalized their disbelief. What happens, though, when the skepticism increases? God bumps up the evidence. And he's been bumping it up like crazy. And it's in the last few decades, especially, it's going up exponentially. It's going up explosively on every order of magnitude. The more we learn about the cell and everything else in the microcosm, the more impressive it becomes. So as Michael Denton put it, the cell, that undirected natural processes somehow turn lifeless chemicals into all the extraordinary complexity of living things. He calls this, he says, this is no more or less than the great cosmogenic myth. In other words, they're trying to eliminate that God's creation with the idea that lifeless chemicals did it. See, it's a myth, he says, and there's good reasons for it. So in Franklin Harold's book, The Way of the Cell, he describes the cell as a single-celled organism, as a high-tech factory, complete with artificial languages and their decoding systems, memory banks for information storage and retrieval, elegant control systems for regulating the automated assembly of parts and components, error, fail-safe, and proofreading devices utilized for quality control, assembly processes involving the principle of prefabrication and modular construction, and a capacity not equaled in any of our own most advanced machines, for it would be capable of replicating its entire structure within a matter of a few hours. There's nothing like this. And the more you look at it, every single cell of your 100 trillion or so cells in your body is more complex than the city of Atlanta. And I'm not exaggerating. The plumbing, the transportation systems, the information systems, and so forth, it's beyond imagination. And the more we're learning, the more it's almost frightening. Nobody has a clue as to how all this could be. It was supposed that it was simple, because Darwin thought of that the cell was just basically a blob of protoplasm, and it was just some goo and some like Legos. So it was like, by analogy, it's like a bunch of Lego blocks. It turns out that each Lego has the complexity of a whole body, miniature body, and the more we learn about the cell, the more extraordinary it becomes. It's interesting. Thomas Nagel, he's an atheist, and I read his book on this matter because he argues why the Darwinian theory is almost certainly wrong. That didn't win him points in the academic community, but they can't refute him. So I love the fact that he's open to this fact. He says, for a long time, I've been skeptical of the claims of traditional evolutional theory to be the whole story about the history of life. He goes on to say it potentially can be scientific to argue that the data of DNA and life points to an intelligent designer, even as science cannot tell you the identity of the designer or what is going on in the designer's mind. That's pretty impressive. I don't know why he still calls himself an atheist, but by the way, atheism's a problem because you're trying to prove too much. You're trying to prove a universal negative. It's better to call yourself an agnostic. You can't know, or you may not. You don't know, or no one can know. Two different versions, but don't worry about that. But at the end of the day, what would it take to get one living cell? And that's the question we're going to look at. Because you cannot appeal to neo-Darwinian mutation and natural selection. Why? Because it has to be alive for that to be the case. So we can't appeal to that thing. You need to go back to chemistry and molecular biology, and that's where Michael Bee's excellent book, which came out a number of years ago, and it really affected my thinking, was called Darwin's Black Box. It was written by a molecular biologist, Michael Bee. He called the cell, it's Darwin's Black Box, because to Darwin, the cell was just that blob, as I said before, protoplasm. And so the supposition that the cell could evolve was not a problem for him. Now we've peered inside that box, and we use innovative methods, X-ray crystallography and nuclear magnetic resonance. And we've been able to delve deep enough to find that the cell is exquisitely elegant. And in fact, it's more complex, as I said, than a major city. And so when we go to this thing, we're going to be going from the cell complexity and elegance. Human engineering and technology has never been able to design anything even remotely like the complexity of a single cell. And we can predict that many new, complex, and elegant features are going to be discovered. So it's an exciting time to live. The last 4 or 5 decades is, again, a plethora of new things that you could have never have imagined. So we're out of time here, but it gets us started in that. So we're going to go from there and look at the nature of proteins first, and how do you synthesize a protein, and what does that look like? And we're going to be talking about the amino acids and all that. You're going to love this. You're also going to like the fact. You're going to like the fact that all your proteins are all the amino acids are left-handed. But in nature, though, they can appear just equally likely left or right. They're it's a chirality. It has to do with mirror images. Why left-handed? So if you had a small protein of only 400 amino acids, it's like taking a fair coin and tossing it 400 times and getting heads. Make you suspicious. We'll stop there.